hope you're all recovered from the poster session. I guess I should probably go ahead and start. I don't know if we're filming. Hopefully not. Oh, we are, okay. So I want to wrap up what we said about spin chains and give one more example of topology and how it's useful. So we're talking about one-dimensional quantum antiferromagnets. And the main point of last time was this explanation of Haldane, before people knew the answer by any other method, of why integer spin chains and half-integer spin chains are different if I just focus on the first term, which is usually the most physical situation. The answer is that half-integer spin chains have this kind of topological term, a so-called theta term, that matters. It modifies the behavior of the nonlinear sigma model, and that doesn't happen in integer spin chains. So integer spin chains, in a sense, are simpler. They just become gapped, while half-integer spin chains are more complicated. So if you then go to a physical spin chain for spin 1 and ask about the phase diagram, you get the following picture. And the one thing I want to explain, because it has kind of a topological explanation also, is if I look at the critical points where the gap in the Haldane phase goes to 0, these are two one-dimensional quantum critical points, but they're different. They're kind of labeled by different combinations of a Lie group and some integer subscript we call the level. I want to explain what this means, because the kind of field theory that was written down to solve this problem is just very similar to what Haldane did, but just a tiny bit more complicated. But it uses the kind of topological facts you already know. So that'll be the last thing we say about spin chains. This is going to be, these points are what are called Wess-Zumino-Witten models. But basically they're the simplest one-dimensional quantum critical points, so-called conformal field theories. Conformal field theory basically means scale invariant, gapless, having a single velocity. These points are mathematically important because they have this very high degree of symmetry. In fact, that's how we're going to motivate them. So I'm not going to tell you the explicit, solution. AKLT is easy to solve. These points are actually quite hard to solve if you just, you see I fixed the 3, now it's 2. If you just plug in the right value of alpha and crank away, it will take a long time to find the solution, but at least the field theory at those points is pretty easy to write down, and the topology you already know is what you need to have that field theory make sense. So the second part of the talk is the main part of the talk, which is on trying to make a universal effective theory of fractional quantum Hall states, at least simple ones, and then I'll wrap up with lists of some things I wish I could have covered, and then lists of things that we don't know, or at least I don't know, that are puzzles that maybe you can figure out. Okay, so to motivate what is going on at these 2 points, let's remember what we said about the Haldane case, which was that in general, if we've got the 2D, that is, for us we're doing one-dimensional quantum systems at 0 temperature, so this is 1 plus 1D, nonlinear sigma model for a curved manifold. And curved means in the sense of having real Gaussian curvature, so not the circle. And what does this mean? Or why would this be true? Well, if we think about the sphere, that was Haldane's case. The idea is that if I think about, this is actually why it's called the nonlinear sigma model in general. If I think about trying to expand my theory in the vicinity of 1 point. So we'd like to do some kind of representation of the field, say, let's say one direction. If I look down on the North Pole, it'll look like a plane if I'm close to the plane, and there would be 2 independent directions, say, phi x and phi y, where these are meant to be 2 perpendicular directions on the surface. But because this is curved, they start to have nonlinear terms once I move a little bit away from the top. In other words, there are interactions between the soft directions on this manifold, and that's what the gap comes from. So it's nonlinear in the sense that once I start expanding around this point to 4th order or so, I'll get interactions, and those interactions turn out to give me a gap. But the example of Haldane shows that there's a kind of a way to fix this. Maybe if you have the right topological term, that will combine with the nonlinear sigma model to give you something gapless. And then they sort of knew that had to work because of Betha's old solution showing that the one-dimensional Heisenberg antiferromagnet was gapless. But it kind of raised a question of, what if I have something more complicated than the sphere? And the case that is most relevant for physics seems to be, let's try to make a nonlinear sigma model with high symmetry. So we're going to make a model where the field is a Lie group SUN. And you can do the same thing I'm going to do for other Lie groups as well, but let's say that we've got some field little g in SU2. So topologically, SU2 is very much like S3. To be precise, I think there's a discrete modding by Z2, but that doesn't matter for pi 2 and pi 3. In general, this dividing by Z2 means that the points that are opposite on S3 wind up being identified. At least I think that's the case. But anyway, it doesn't matter for higher homotopy because any discrete modding doesn't change any of the pi's after 1, a useful fact. So that means that pi 2 is equal to 0 for SU2, and in fact for SUN, n greater than or equal to 2, and pi 3 is equal to z. Okay, we sort of used pi 3 equal to z once before, but I didn't give you an explicit formula. I am going to give you, we're going to wind up with something a little bit explicit in a second, but the way we use this was related to the fact that there are gauge transformations of the Chern-Simons integral in the Brillouin zone that describes the 3T topological insulator. There are gauge transformations that are not contractible to 0 in the same way that for the polarization integral in 1D, pi 1 was equal to z. So this invariant was related to the fact that we could change the Chern-Simons band structure integral by 2 pi n. So theta, the magnetoelectric angle, could be changed by 2 pi n. So for now, if we were to try to write down a simple kinetic term, the simplest possible field theory in terms of G, well, let me point one thing out, which is that if I want dx theta, a simple way to write that is as, well, there's a factor of I in front, but e to the minus I theta dx of e to the I theta. So that'll give me I dx theta, because when I pull this down, I'll get I dx theta times e to the I theta, and the e to the I thetas will cancel out. And this I could think of as G inverse partial xg, where e to the I theta is an element of simply U1, the unitary group of 1 by 1 matrices. So this is a way to get out one part of a kinetic term. In general now, G's are matrices, so this is some matrix. I've got a matrix inverse times a matrix. I need to get from two matrices back to a number, and the easiest way to do that is the trace, and that motivates the following complicated theory. So the first part of the theory, it's not that complicated, but I wrote it up to save me some time. The first part of the theory is what you would guess if you just tried to write down a simple generalization of the circle to SUN. And then the rest of the theory is what we're going to explain. It's a famous term written down by Wess and Zumino. So we're trying to understand, again, what are these gapless points of the spin 1 chain, and are they different from each other, and are they different from the spin 1 gapless chain? The spin 1 gapless chain would already be gapless at theta equal to 0, which means no biquadratic term. Okay, so the answer, which is our last example of a topological term before we get to a fully topological field theory, is this Wess-Zumino term. And what it does in this context was sort of contributed to by Witten. So this kind of model is called a Wess-Zumino-Witten model, or just WZW model. But let me just explain the notation. So this first term, forget about the second term. Don't be scared. So the first term, k is some integer, and we'll explain why it's an integer in a second. This term, k, it's sometimes called the killing form, but basically it's just a trace with some normalization related to which SUN I'm talking about. So for any n, I define this thing, which is just the generalization of the kinetic term. And I did one last thing. I wrote it the way particle physicists write it to emphasize one difference that they sometimes talk about with topological terms. Here I've got an upper index and a lower index on the derivative, which, if you like, means that I use the metric tensor to raise the index on this one. So there is a metric that appears in defining the kinetic term of a field theory. So in particular, if I made some complicated coordinate change to curve space, something about the metric would show up. The second term, the Wess-Zumino term, doesn't have a metric. You could think of it as, instead of using the metric to raise or lower indices, I'm just using this epsilon ijk term. So I want to explain what this is, what it's doing, and how it's very much like the Haldane term, and how, in fact, the way this term works is what quantizes k to an integer. And this is the term that winds up keeping the theory gapless. So k, just looking ahead a bit, that's that subscript that appears, the so-called level. So this is the SUN level k Wess-Zumino-Witten model. So it comes up in spin chains. In fact, the same algebra, which is called a Kac-Moody algebra, it's sort of a combination of criticality, which is labeled by something in one dimension, one spatial dimension called the Virasoro algebra, and SUN, a Lie group. This actually comes up in the classification of anyons. So there's a chance that Adi Stern, for example, might talk about the same mathematical object, even though the physics context is quite different. So, okay, why is this term even sensible, and what does it mean? And the first thing that's very weird about this term is this is an integral where it was originally a two-dimensional theory, so it's defined on R2, the plane. G was a function of x and y on the plane, say. For simplicity, we think about it as compactifying space-time. Let's assume that all the fields at infinity are constant, so I can think of the theory as defined on the surface of the sphere in 3 dimensions. This term, there's no really compact, or as far as I know, there's no really way to write it directly on the surface of the sphere. Instead, we have to fill in the sphere. So we basically continued, and this is a strange thing, but it winds up being useful actually in some topological insulator calculations and things like that, so I want to explain it. We continued the field G, and we need to see that this makes sense, from S2 into the interior. So B3 means the unit ball. It's like the inside of the unit sphere in 3D. So what I drew here, this would be S1, and inside that would be B2. So that's the idea, except go to one higher dimension. So what lets us do that? What's the topological fact that says there has to be at least one way to continue the field from the surface of the sphere into the inside? Well, think about, as I move from the outside of the sphere to the center, think about a series of spherical shells that are getting narrower and kind of evolving continuously. So that's a continuous change of the map from S2 to my Lie group, SUN. If there was no way to make that into the constant map, which would be that all of S2 is going to the constant value, which is the value at the center of the sphere, then that would be saying that the surface of the sphere is in a different topological class from the constant map, which would mean that pi 2 is not equal to 0. But pi 2 is equal to 0, so this is a way to think about pi 2. If pi 2 of something is trivial, then that means that if you have that field defined on the surface of a sphere, well, there's a way to make that smoothly deform to the constant map on the surface of the sphere. And you could view that as the series of shells you get moving inward from the sphere to the center. So it'd be like here, if I had a map from the circle to something, then here, this is a slightly different map from the circle to something. This is a slightly different map, and so on. And eventually, I only have a point, so it must be the constant map. So this kind of continuation into the bulk exists only if, we need to use the fact that pi 2 of SUN is 0. Now, the second question you should worry about then, whenever you do this trick of taking your theory defined in one space and trying to make it defined on a bigger space for nice topological reasons, is it unique? So that says that there is a continuation. To be precise, we should say, is the physics unique? And the answer is yes, if k is an integer. And let's explain why that's true. So this is a little bit, only a tiny bit different from the Haldane term. The Haldane term, whenever I gave you a configuration, gave me an integer. In this case, what's going to happen is that if I give you two different continuations, this term isn't always an integer, but it has a neat property. It's exactly like the polarization in Chern-Simons integrals we wrote down before. If I give you two different continuations, I want to try to convince you that the difference between them will be a multiple of 2 pi n if k is an integer. So when I put this thing in a quantum path integral, it won't matter. So in other words, there are different continuations, but they only shift the integral by a multiple of 2 pi, which means once I stick it in a path integral, I'm okay. So here's why, and this is kind of a neat topological fact. Suppose I have two different continuations of the circle into the interior, and I want to think about the difference of them. Well, this object, the answer to the question mark, is let's go there. Think of it this way. The sphere, sorry, not used to color chalk here. The sphere where this is the equator, so these two agree on the equator. Think about taking this disk and kind of puffing it out into a hemisphere, the northern hemisphere. Think about this disk and making it the southern hemisphere. I can make them agree on the equator because they both have the same boundary. They're both continuations of the same theory on the boundary. The meaning of the minus sign is that they're oriented differently with respect to the equator. So in other words, the difference of two B2s, two two-dimensional unit balls, is an S2. The same thing works in one higher dimension. So actually, the difference between two continuations, in a sense, call it B3A minus B3B, that's a three-dimensional sphere. And if I ask, what in the world is this object? Well, I won't prove it to you. This mathematical object is what computes pi 3 of SUN, which is an element of Z. That is, the difference between two continuations into the unit ball, I can take those two continuations and combine them. The difference is a map from S3, not S2. Now it's S3 to SUN. We know those maps are labeled by an integer because we said pi 3 of S3, or indeed pi 3 of this for any n greater than or equal to 2, is equal to Z. So this thing is basically just the topological invariant that computes the map S3 to S3, if I took the simple case of SU2. In general, it's what computes pi 3 of the Lie group. So even though it looks complicated, if you're willing to believe that what you know about the 2-sphere kind of makes sense for the 3-sphere, then that's all this object is. And this is the Wess-Zumino-Witten model in 1 + 1 dimension. So it's a very important example of a gapless field theory with a slightly different kind of topological term that is more complicated than the term in the Haldane case, but now I think you know enough topology to understand why it makes sense. And then one last comment on physics before we get into the quantum Hall effect. I said that these are different points, so one of them, if you want a rough picture of what level is, so with spin equal to 1, there were 2 points, SU3 level 1 and SU2 level 2. The S equal to 1/2 case is SU2 level 1. In other words, this is the betha. With theta equal to 0. That is no biquadratic term. So in a way, the relation between these two, it's the same group at a different level. That's kind of like spin half and spin 1 being different representations of the same symmetry group. A way to tell that all of these are different is to look at what's maybe the most important property of a one-dimensional critical theory like this. So again, if we didn't have the topological term, we'd just get a gap. This turns out to be the right topological term to make this theory gapless. And a measure of how many degrees of freedom are gapless is the central charge. So this is a nice thing about 1 plus 1 dimensional field theories. It was recently shown also to work for 3 plus 1 dimensional field theories. Central charge is how many degrees of freedom are gapless in units where central charge equal to 1 is a free boson. So for example, the height model that came up in frustrated magnetism, that's 1 free boson, that's central charge equal to 1. If you take somewhat more complicated frustrated magnets, you can get C equal to 2 or something. Here, this is also C equal to 1. Of these, this one is, well, let me give a general formula and then we can check it. This one is C equal to 3/2, and this one is C equal to 2. So they really are different. For example, the central charge is what you see if you measure the specific heat at low temperature, assuming you know what the velocity is. So it's maybe the most important number about a critical theory in 1D is the central charge. And these are really 3 different critical points in 1D. So the... Yeah, let me not try to... Okay. So let's work through this and figure out what the missing part must be. So if I do SU2 level 1, then the denominator is 1 plus 2, which is 3. The numerator is the dimension of SU2, which is 3. If I do the, maybe it's K times that. If I do SU2 level 2, I get 2 times 3 over 2 plus 2, which is 6/4, which is 3/2. And if I do SU3 level 1, yeah, maybe this is only for SU2. Yeah, for SU2 it's 3K over K plus 2. And I'm not sure if I remember the general formula. Okay. So I think that's all I wanted to say about spin chains. Now I want to jump back to the fractional quantum Hall effect. So if there are any questions about spin chains, I was trying to write the central charge of the Wess-Zumino-Witten model, but I only remember it for SU2, I realized. Do you remember it for SUN? No. Okay, so then we're safe. Actually, I do. No, I do know what it is. It is. No, I had it right. Good. K dim G. So I had it right, but I got nervous because all of you, I thought, might know better than me. K dim G over K plus, or K dim SUN over K plus N. So it is what I wrote down. So, okay. Oh, sorry, did I not write clearly enough? Or? What was that? Okay. I'll write it in large letters in a second. So it is central charge of SUN level K was K times the dimension of SUN as a Lie group or Lie algebra divided by K plus N. I'll leave it for you. Okay, so that's spin chains.
Before you cross it off, rub it out. So the argument that makes K an integer.
Right.
And in particular, what is it that ties the K's in front of the two terms?
I didn't explain the second part. The second part is harder, and I don't know if that... Okay, the first part is K had to be an integer because... So K is basically multiplying, to be precise, the difference between two continuations. Should be unphysical. I mean, it shouldn't do anything. Which is true if the total action, if I have e to the, let's say we're in Euclidean space. It should be true that if I look at the difference in the path integral between one action and the other, I get a multiple of 2 pi I. Let's write it this way. And the way I defined the coefficient k over 24 pi, the 24 pi is chosen so that the difference is e to the 2 pi I n times k. So if I take n equal to 1, for example, there will be a difference unless k is an integer. So that's what quantizes the level. As far as why that forces something about the first term, well, that gets into... The terms should scale in the same way because the second term has to be keeping the first term gapless. Like if I kept the second term constant and made the first term very big or something, then the second term's effect on the first term would be small. So they both have to scale with the same coefficient. Precisely why it's that relation between the first term. So they're both linear in k. Beyond that, I don't know how to say why it's 1 over 8 and 1 over 24 without some big calculation. So that's enough with one dimension. So one sense you might have gotten from this is that 1 plus 1 dimensional field theories, even though there are giant books on them, they're solvable in many cases, but they're not easy. What about 2 plus 1 dimensional field theories? Those must be really hard. Well, most are. In general, there's no magic bullet for 2 plus 1 dimensional field theories the way there sort of is for 1, but there is an exception. So let's try to make a theory for the quantum Hall effect. Both integer and fractional, but where it is really powerful is for fractional. Integer, I guess we don't need anything fancy. So we're going to start, motivate it, by flux attachment. Which is about statistics of particles. And this idea, I'll try to give you some intuition before we start writing down equations, but the idea is that in 2 plus 1 dimensions, if I want to convert between bosons and fermions or anyons or something like that, the idea is to attach a gauge field to particles to imitate statistics. So for example, instead of fermions, I could have bosons with this particular kind of gauge field. And then we should check that the theory we get from this idea. So it is possible to sit down with the electrons and carefully try to derive the Chern-Simons theory, at least in some simple cases, but it's beyond the scope of a lecture and very tedious. So I'll do what people did historically. So in the mid-'80s, people guessed, maybe starting with Gervin and McDonald and then Zhang, Hansen, Kivelson, and Reed, people used kind of physical arguments to figure out this was the right theory. Then people confirmed microscopically it was the right theory, but they also found some new properties that they hadn't really realized about the quantum Hall effect before that came out of this theory. So checks are, it should give an edge mode on a, well, spatial manifold with boundary. That just means something like a disk that has an edge. So, somewhat unnecessarily complicated language. So the time direction is always going to be r. The spatial direction, I'm going to be interested in the differences between the sphere and the torus. With no boundary, like the sphere or the torus, I should get a ground state degeneracy. And then various other things one could look at. It should give a quantum Hall electromagnetic response. So we already said that if I have an electromagnetic Chern-Simons term, that describes the quantum Hall effect as in terms of its electrodynamic response. But we want to do more. So I'll explain that later on. Okay, but before getting into the equations of the theory, let me just explain why flux attachment is actually a useful idea, even if you want to understand just qualitatively all the other quantum Hall plateaus than nu equal to 1 over m. So far we wrote down the Laughlin state. So I want to give a picture where you could call this a heuristic composite fermion picture. At least one form of this is due to Jane. How is the fractional quantum Hall effect? Okay, there's a cute picture for how that might be related to the integer quantum Hall effect. And what are other fractions than 1 over m? So there is a way to use this idea to write down explicit wave functions for other fractions. That's what Jane did. But for now, let's just try to figure out, if I think about this idea of attaching fluxes to particles, and in this case it's going to be the real magnetic flux. We're going to do it with sort of artificial flux in a second. But let's just think about what is the integer quantum Hall state to start with. So the integer quantum Hall state, in terms of counting, well, one filled Landau level is 1 electron per flux quantum. So this would be 6 electrons with 6 flux quanta. So these arrows are flux quanta. These dots are electrons. Okay, so what does flux attachment mean? Well, suppose I want to get a picture of the Laughlin state. So the Laughlin state, I don't have as many electrons. got 1/3 as many electrons for the same number of fluxes. Well, in what sense is this at all like the integer quantum Hall state? And here was the idea. Think about composite fermion means this combined object of an electron with two flux quanta. So what I mean by combined object, I want to imagine that these flux quanta are kind of merged into a solenoid attached to the particle, and ask, how would another electron see that? And to understand why two flux quanta, let's compare moving around a flux quantum, the Aronoff-Bohm effect of moving around a flux quantum, to one fermion moving around another fermion. Okay, so if the claim, I'll let you check this for yourself. An electron moving around an electron plus two flux quanta has the same statistics as if I just moved around an electron. So the fact that there are two flux quanta means I'm back to where I started statistics-wise. So that means that I could think of this object as something, it still has charge E, but it's not an electron, it's something more complicated, it's a composite fermion, but I've got composite fermions that are now moving in a background of one flux quantum left per composite fermion. So, in a sense, the fractional quantum Hall effect of electrons is like the integer quantum Hall effect of this composite fermion. So if that just gave you the Laughlin state, maybe it wouldn't be so exciting. But the thing is, you can now generalize this idea. So suppose instead of 2 electrons for 6 flux quanta, I took this away. So now I've got 2 electrons for 5 flux quanta. So this is a state at nu equal to 2/5. But what does it look like? Well, it looks like I've got 2 of my composite particles, 2 composite fermions with 1 flux quantum. Well, 2 particles per 1 flux quantum is like 2 Landau levels. If 1 particle for 1 flux quantum was like 1 Landau level, so nu equal to 2/5 is like nu equal to 2. So in particular, so that what this leads, let me call it a picture, is that nu equal to 1 is like nu equal to 1, well, nu equal to 1/3 is like nu equal to 1 of composite fermions. Nu equal to 2/5 is like nu equal to 2, nu equal to 3/7 is like nu equal to 3, and maybe the most important qualitative prediction of this picture is that these numbers are getting closer and closer to 1/2, so that maybe nu equal to 1/2, well, that would be like filling an infinite number of Landau levels, or it's basically like the Landau level splitting has gone to 0, and that's like a Fermi liquid. So people sometimes describe, if I don't turn on any superconductivity or anything, if I have a gapless state at 1/2, then that is a Fermi liquid of composite fermions. So it turns out that this is unstable to a very exotic gap state, the first non-abelian state, maybe not at 1/2, but indeed at 5/2. So at least as a precursor, this is kind of consistent with the statement that even denominators don't have this kind of fractional quantum Hall state, but you can get an awful lot of odd denominators. And in fact, the fractional quantum Hall states that are seen most strongly in experiment are this sequence and its particle hole conjugate, which are called the main sequence. If instead you wanted to make the 1/5 state, well, then we would make yet another kind of composite fermion. We would gather together 4 flux quanta and 1 electron. So that's again back to a fermion. So this would be the composite fermion picture of the 1/5 state. So just by drawing pictures and by doing one calculation, which is that 2 flux quanta get you back to being a fermion, or 4 flux quanta, or 6, or whatever, you get surprisingly much out of the simple picture. You get a prediction for other quantum Hall states. And in fact, maybe an argument that this connection is more than just playing around. If you look at the edge, So a nu equal to 1 state, in the simplest case, has 1 edge mode. A nu equal to 2 state has 2 edge modes. A nu equal to 3 state has 3 edge modes, which you can think of as my 3 Landau levels crossing through the chemical potential at the edge. Well, it turns out from the fancier theory, Chern-Simons theory, that this also has 1 mode, 2 modes, 3 modes, and so on. So really, this is analogous to that at some deep level.
So
yes?
By playing with this, can you get absolutely any fraction?
If you go to...
fractions that you cannot get.
You have to do higher versions of this, but I mean, in this simple picture, I don't see how you would get something between 1/3 and 2/5. But what you can do is what's called a hierarchy. So before composite fermions, there was a different... In fact, the strength of composite fermions over the earlier picture, which was the Haldane-Halperin hierarchy, was that composite fermions gave you fewer fractions. That one does actually give you everything. So I'm going to... At the very last thing I do is going to be tell you what a K-matrix is. If you make enough particle types and a large enough K-matrix, you can get any fraction you want.
So it's like string theory.
Well, what's predictive, though? It may be true. I mean, if you look at the experimental data, every time we make a cleaner sample, we get more fractions. So, what is predictive about either approach, though? Well, okay. So, first of all, in the composite fermion picture, it was originally thought, this is perfect. This only gives us the fractions that are seen experimentally. But it turns out there are a few fractions, like 4/11, that you don't get in the simple way. You basically have to make a hierarchy of composite fermions to get things like 4/11, which are seen weakly experimentally. But what's predictive is that the smaller K-matrices, or maybe even more predictive is this composite fermion approach, these are the strongest plateaus. But I don't think we understand yet. I'll put it this way. I don't know of any odd denominator that we will never see as we make our quantum Hall sample cleaner enough. So the fact that the theory, if I keep going and going and going, will eventually give me all odd denominators is not necessarily wrong. But what seems to be predictive is that the simplest things are the strongest plateaus. And in numerical diagonalization, the most robust states. But good question. Yeah?
So because at very small thing, we should get the Wigner crystals.
Yes.
So, I mean, at some point it should break down.
Yeah, this isn't necessarily the ground state. This is a way to write down states, but you have some complicated energetic question about whether it's the right state. Yeah. So you have to eventually do numerics. Yeah.
So you said that electrons which find flux quanta, it doesn't change the statistic?
Well, an electron moving around 2 flux quanta gets you back to fermionic statistics.
What about bosons? If you have bosons finding flux quanta?
If you basically, 1 flux quantum is enough to switch you between bosons and fermions, and 2 flux quanta get you back to being a fermion.
Why?
Well, okay, think about the Aronoff-Bohm effect. This was the calculation I wanted you to do to convince yourself, but I'll tell you. So the idea is... The point is, I guess, if I think about moving a particle around a flux and exchanging 2 fermions, they're kind of similar. So let's take the simplest case. Let's take a boson plus a flux quantum and compare it to fermionic statistics. Well, okay. Before we do that, the Aronoff-Bohm effect is if I've got some flux here, and I think about moving an electron all the way around, then the idea is in that process I pick up a phase. I will get back to 2 pi if I move all the way around for 1 flux quantum. So that's what I mean by Aronoff-Bohm effect. Now, how is this like the statistics effect of fermions? Well, the way we normally state that is an exchange. Which is that if I took 2 identical fermions, A and B, well, an exchange is not moving one of them all the way around the other. It's like half of that. So an exchange would be like this. So I haven't quite moved one all the way around the other, but I've done half of that. And that process gives me a -1 for fermions. Or moving all the way around would be like an Aronoff-Bohm effect with one flux quantum. So that's why, in a sense, adding a flux quantum moves you back and forth between bosons and fermions. And you can do the calculation a little bit more precisely if you want, but this is the basic idea that what we're going to do in a second is find a way to attach Aronoff-Bohm flux to particles. So that was my picture. We need to do some math, but the picture was that I've stuck my flux lines on the particles, or at least some of the flux lines, so that when another particle is moving around, it sees the combination of the original particle and the flux lines, which means that now the total effect of moving one particle around the other is to combine this and that. And then the only remaining thing is the counting, to get the counting right, and that you can work through. But the key thing to remember in the counting is basically that an exchange is not all the way around, it's halfway around. So that's the one hint I'll give you. So that's the sort of spirit of changing statistics by flux attachment. And now we want to make that happen. So this is actually how people were led to the kind of theory. And again, I think I've repeated the motivation before, but we want a theory that captures the essentials of the quantum Hall effect in the same way that Ginzburg-Landau captures the essentials of symmetry breaking. What's tricky, what people realized, is that the field that appears has to be a gauge field. So the clever idea that people had was that so I'm going to go back to the Laughlin state. Forget about all these states that are more complicated with multiple components and all that. I want to start with, so this is a 2 + 1 dimensional Lagrangian. Gamma is some so far undetermined number that I want to fix later. Fully antisymmetric tensor. Little a is a 2 + 1 dimensional gauge field. And I couple it to my quasi-particle current. So this is quasi-particle density in the 0th component and so on. So little a is kind of like big A. Big A, the electromagnetic vector potential, except that here, before we thought about a term like this for big A, we added a term like sigma xy AdA for the electromagnetic field to 3 + 1 dimensional electromagnetism. Little a is different. It's sometimes called internal gauge field or statistical gauge field. This is like the order parameter. It's not an order parameter, but it's the field that we're using to describe the electrons of the system. So this is some U1 gauge field living in 2 + 1D. When I say gauge field, I mean we should think about a gauge invariance just like in electromagnetism. And we'll see in a moment that a nice feature of this theory is related to the fact that it's almost, but not perfectly gauge invariant. Normally we want physics to be gauge invariant, so there ought to be something we have to fix then. Okay, but flux attachment, well, the first thing to note is that this coupling is like what you're used to when you think about a particle moving in a gauge field. So from the particle's point of view, this is like any other gauge field. So when we think about electric and magnetic components of A and so on, so in 2 + 1 dimensions, there are 2 electric fields and 1 magnetic field. This particle sees the gauge field A just like it would see an electromagnetic field. However, let's figure out how does the gauge field see particles, because that's a little different. So, does this attach flux to particles?
And the particles here are carried out
Actually, I think the right way to think of them is as Laughlin particles, but I haven't done anything that would fix that yet. Let's say there's some kind of matter. I think it's probably true that originally people were thinking of them more like composite fermion, but I think the right thing is going to be to think of them as the Laughlin quasi-particles of the theory. But I haven't fixed that yet. So there's some kind of particle. Let's just leave it at that for now. So the spirit is going to be that the fundamental bulk excitations of the Laughlin state are not the electron in the hole. They're the quasi-particle and the quasi-hole. The quasi-hole is the thing I wrote down to you before with charge 1/3 of a normal hole. And those, we want to find out, how does the statistics of those depend on this parameter gamma? So, okay, what does this theory do? Well, the equation of motion for the theory, let's think about just static particles. So suppose J0, that's the charge density of particles. So to get an equation of motion that involves J0 in it, I'm going to vary with respect to A0. So if I vary the term that matters, think about this. So I've got 0, 1, 2 are my three indices. If I think about A0 in the first slot here, so when I vary with respect to A0, I'll get something. If A0 were here, I would want to integrate by parts, and then I'd get back to where I started. So if A0 is here, and I take the derivative with respect to A0, then I get so vary with respect to A0, and I get epsilon ij di aj, where I are spatial indices. That is not the zero component. So mu and nu, Greek indices are 0, 1, 2. Roman indices are 1 and 2. And this is just going to be related to the magnetic field. So the full equation is going to be 4 gamma epsilon mu nu lambda d nu a lambda is, I think if I did it right, minus j mu. So this is the equation of motion for the A field. Particles sitting at rest, then only J0 is non-zero. And what we've got is that a particle sitting at rest gives me a magnetic field. So that part is different from ordinary electromagnetism. So this combination of the curl of A is what we think of as the magnetic field. Normally we have to move a particle to get a magnetic field, but in this theory that's not true. That's the first clue that this is not different from, that this is a lot different from Maxwell. So even a particle sitting at rest is tied to a magnetic field. So B, which is this combination, is proportional to charge density of the particles. So then, if I remember, there's a connection between how much flux I attached, which is 1 over gamma, and the statistics, then I ought to be able to work out a relationship between gamma and the statistics, and that relationship is, to be precise, that the theta, the statistics angle I defined before, which is that exchange of two particles gives me an e to the I theta, that is 1 over 8 gamma. So in other words, we can eliminate the one free parameter we had in the theory if we know what statistics of particles we want to describe. In the simplest case, as a check, this theory ought to work for the integer quantum Hall effect if I just put in ordinary fermions. So with 1 over 4 pi here, that is with this prefactor equal to 1 over 4 pi because we want theta equal to pi. So let's work it out. If we do gamma equal to 1 over 8 pi for fermions, then I've got 2 over 8 pi, and the prefactor just becomes 1 over 4 pi. So for the one state that we know best, the integer quantum Hall effect, for the integer quantum Hall effect based on Fermi statistics, we would get L is 1 over 4 pi and in that case J really is just ordinary electron current. Well, so what if we want to describe a more complicated state? Well, what we should check is that this theory reproduces the things we want to be true about the state. So the statistics angle so far could be just any number, and you can put in even some irrational value of gamma or something, but those, at least in abelian Chern-Simons, nothing quantizes the angle. In other theories, like Wess-Zumino-Witten, something gets quantized. We have to put in some physics, and the physics is going to be one number for the Laughlin state. So we, instead of 1, we put k for nu equal to 1 over k. So I said we're basically going to guess a theory. We'd like to verify that now this gives me some of the physical properties I expect for the Laughlin states. So all I've done is change one integer to get from integer to fractional states, at least the simplest fractional states, and those fractional states now will have fractional statistics in general. If I want to describe nu equal to 2/5 or 3/7 or something more complicated, but we think almost all, probably all of the quantum Hall states that are observed except for the even denominator ones. So it was hoped that there would be odd denominator, even more complicated states, but those are hard to see experimentally. So all the odd denominator states, which is 95% or more of all the states we see experimentally, are described by a slightly more general version of this theory, where I have multiple A fields So what I've done here is just say, this was if I have one kind of quasi-particle. So in the Laughlin state, well, there's to be one kind of quasi-particle. I don't think about the antiparticle as different from the particle for the purpose of this counting. When I go to something like the 2/5 state or the 3/7 state or so on, or even if I go to the integer quantum Hall state at nu equal to 2, then I should have different kinds of quasi-particles. And so to do that, K, I put an upper index on A to describe the gauge field associated with different kinds of particles. And now this one integer that describes statistics before is now turns out to be symmetric matrix. So this is the full abelian Chern-Simons theory. I think everything I'm going to do until the very end is just the one component case. But going to higher components is not that difficult. And actually, one reason why we care a lot about this higher component theory is that some other models you'll be hearing about, like I think someone's giving a tutorial on the Kitaev toric code, that's described by a 2x2 K-matrix that maybe I'll write down later. So that's the kind of simple generalization if I want to have more than one different kind of quasi-particle. Okay, so let's analyze this theory a bit more at different K. So far we've said K affects one thing, which is the statistics of particles. I said that this theory was almost gauge invariant. If someone gives you a gauge theory, it would be good to check that it's gauge invariant. So let's think about this term and how it's different from Maxwell. So Maxwell, remember, is dA, dA. That's nice and locally gauge invariant. You make your gauge transformation on the potentials, and E and B don't change even one little bit. That's not quite true here. So let me focus on the first term. Forget about the matter for a second. So if we took this term, gauge transformation was A mu goes to then what happens to that? Okay, so we've got one term which is the same thing back again. Plus where I made the gauge transformation in the first term. Plus where I've got the gauge transformation in the second term. Okay, so of these terms, this one is not a problem, because remember, the epsilon tensor is anti-symmetric under exchange of any two indices. So if I exchange nu and lambda, this is anti-symmetric, this is symmetric, that gives me 0. Partial derivatives commute. So I don't need to worry about this. This one could be a problem. It's not a... Whether it's a problem or not actually depends on what manifold we're talking about, and it turns out that this is not a bug. This is arguably the most important feature of the Chern-Simons theory. So if we think about this term, let me write it a slightly different way. I could write this as a derivative of epsilon mu nu lambda chi d nu a lambda, because if this derivative were to act on the second term, I would get 0 again by this commutation of partial derivatives argument. So the way we express it is that the theory is gauge invariant up to a total derivative or up to a boundary term. So people sort of maybe were aware of this problem but kind of brushed it under the rug until Xiaogang Wen pointed out that this is a good thing. It means that if I have a theory on a manifold with a boundary, like for example, if I'm on the disk, then the theory just isn't complete. It can't be complete because it's not gauge invariant. there needs to be something extra at the boundary to fix that. In other words, and so what you have to add, well, there's a bit of manipulation you can do to actually derive it. That's in my notes, but let me tell you the answer because it's simple to write. So that, just to restate the argument again, Chern-Simons is not like Maxwell. Maxwell is sort of locally gauge invariant. I make a gauge change and everything is fixed. Chern-Simons, I make a gauge change and if I had a torus or a sphere, everything is okay because then there's no boundary. If I have a disk or anything with a boundary, there's a problem. The term that fixes this well, one thing is that it should be linear in K. It's a pretty simple theory. It's a free boson on the edge. Let me comment on this theory in a second. So we had a 2 plus 1 dimensional bulk theory because the spatial manifold was 2-dimensional. Now we have a 1 plus 1 dimensional edge theory. That 1 plus 1 dimensional edge theory, it has to be a little bit strange. So this is the integral of Lagrangian. This is the action. So one thing to note is it has to have the same k in it as the bulk. It has to be proportional to whatever is going on in the bulk because this is to fix something about the bulk. So it's logical that k would be in front. The reason why this term is kind of logical, and the reason why you probably haven't seen this term when you studied Hamiltonian mechanics or something, is that the Hamiltonian of this is 0. So this is the action. If I convert to Hamiltonian, because it's first order in time, normally we deal with things that are second order in time. But this is actually a general feature that sort of had to be true because the bulk theory is purely topological. There's no energy scale in the bulk. The only parameter we specified was an integer. An integer doesn't have units of energy, it's just an integer. So there can't be any unit of energy on the boundary. The part of the boundary theory that comes from the bulk is, in a sense, gapless, but it's definitely gapless, but it's sort of topological. In fact, it's gapless because all the states are 0. So to make it propagate, we assume that the details of edge physics I'll tell you the term we normally write down to make this physical, but this is kind of the unique answer forced upon us. If we have a bulk, there has to be an edge, and the edge has to inherit k from the bulk. So that means, the reason why this is important is I'm going to show you some experimental data in a second. It's hard to probe the bulk of a quantum Hall state because it's gapped, it's almost inert. The edge is gapless. This says that if you could measure the right thing at the edge, you could measure k, which is related to the statistics angle. So that means by doing some kind of edge measurement, you could hope to measure what is the fractional statistics of the bulk quasi-particles. So this is one version of the bulk edge correspondence. So to be a little bit more physical, we write so the second term, V, is some non-universal quantity with units of velocity. and that, well, let's just think about the integer quantum Hall case to make it simple so I don't have to worry. Then this velocity tells me how fast do my excitations move along the edge. This one-dimensional bosonic theory turns out to be equivalent, if I put this here, to free fermions. Moving in d equal to 1. There's a trick to handle one-dimensional fermionic theories by writing them in terms of bosons. This is the bosonized representation, as we say, of free fermions. So it kind of hangs together within the integer quantum Hall effect, the simple picture of the edge. But the point is, even when you don't have free fermions, so even when k is not equal to 1, this is the right edge theory, we think. To some extent, it can be checked numerically and experimentally, and I'll flash up one experimental check. Note that if we go from one integer k to this k matrix, ij, then the number of edge bosons is the dimension of that k matrix. And when exactly there have to be edge bosons is a little subtle. If I have a fully chiral theory with things going in the same direction, there are always just as many edge bosons as dim kij. There are cases where this isn't entirely true. So, for example, the Z2 spin liquid that you've already heard about, for example, the spin liquid that appears in the triangular lattice quantum dimer model, or the Kitaev toric code, you could write K. You'll see that there are two kinds of charges in the bulk, which you could think of as electric and magnetic charges. They're bosons by themselves, but they have a non-zero statistics angle with respect to each other. If anyone does a tutorial, maybe they can convince you of this. I won't try. But this is the K matrix for that, and it turns out this would have one mode going in either direction, but in that case, because it's kind of symmetric between left and right, the two can more or less cancel each other out. There doesn't have to be an edge mode, and in general there isn't. But I guess the point of this Chern-Simons language is that it's a way to kind of unify when we say the quantum Hall effect is topological and we say the Z2 spin liquid is topological. If you want a common language to describe them, that's this abelian Chern-Simons theory. So the last thing I promised... Oh, yes, question.
Before you arise, so how does adding this chiral boson fix the problem of getting...
Can I refer you to my notes, which are even posted already, rather than trying to... Okay, let me see how long it would take me to do. Actually, I have...
Because so far I don't see any coupling of this with
Well, actually, but basically phi came from the restriction of A to the boundary. So let me see if I can do this. Okay. Well, let me answer this one. This is going to take a few minutes, but okay. If you have a quick one while I'm erasing, you can ask.
If I understood well, the edges are residual gauge invariance, but can you know how many channels you have? The new, can you get from this? Or?
Yeah, so it's quite interesting. If you give me the nu, the filling factor, then people have thought for a while and figured out what the K matrix is, probably. And that makes a prediction for the minimum number of edge channels. You're sort of always free to add extra pairs. You could basically add extra wires at the edge that don't have anything to do with the bulk. But yes, if you know nu, we think we understand the quantum Hall states well enough to figure out what is the K matrix and then know what the edges should be. So as a simple example, if I took 2/5, I said before that nu equal to 2/5 was kind of like nu equal to 2, and indeed both of those have two edge modes going in the same direction. If I took nu equal to 2/3, we think that has two edge modes going in opposite directions, And I can make more and more complicated versions of that. But yeah, let me just directly derive that from the bulk. So I'm going to choose a gauge condition A0 equal to 0. In other words, I chose my gauge transformation chi in order to get rid of A0. So the equation of motion for A0 in the absence of particles then becomes epsilon ij aj is equal to 0. So that means that A is the curl of something. In 2D, if I've got a field whose curl is 0, sorry, that means that A is the gradient of something. A sub I is partial I phi. So this is going to be our edge field in a second. Then the bulk Chern-Simons theory was minus k over 4 pi integral. What I'm left with is epsilon ij ai d0 aj, if I did this right, d2x d tau. If I write that out explicitly, that's integral of dx phi d0 dy phi minus dy phi d0 dx phi, which is minus k over 4 pi integral, do this right, partial x phi partial 0 partial y phi minus partial y phi d0 dx phi. There's a dx d tau and a dx d tau. I think you can figure that out. So that looks like this is still a bulk thing, but this is like the curl of a vector field, where the vector field's components are V is then this thing is, so if I take what was down there, that's minus k, and yeah, you don't need to copy this down, it is in the notes, I promise that the notes are up. Now we use Stokes' theorem. So we have an integral of a curl, spatial curl over the two-dimensional bulk. So that's integral over the enclosing boundary minus k over 4 pi v dot dl d tau. And that, once I've written this thing down, let's assume that the boundary runs along x to keep it simple. So I've got that, and one integration by parts gives me dx phi d0 phi, which is what I wrote before. So it can be done.
And if you have matter content, then this phi couple.
That's right. So at the edge, the Laughlin quasi-particles are now gapless. So there is matter at the edge, and indeed, we think of what's really being measured at the edge as being the fact that the edge is not really free electrons, but more like free Laughlin quasi-particles. In fact, there are noise experiments that people try to interpret that way, and the actual experimental status of noise at the edge is quite complicated. In fact, the experimental status of many things at the edge is quite complicated. But what I'll show you is one big success, at least. In the second line. This. Did I mean? Oh, yes. I want that's right, DIAJ. Thanks.
Is that because there is much charge accumulation at the edge?
Yeah, this is kind of the, when I constrain one of these, this is even in the bulk, the equation of motion once I've got a constraint like this, must be compatible with the constraint, and that gives me a requirement, I guess. That's maybe the way to put it. But yeah, anyway, sorry for going through rapidly, but the details, I promise, are in the notes. So that's basically the bulk field got moved to the boundary and became this gapless mode, and this whole combination is gauge invariant. So we just took the last part of the bulk. What if we didn't have a boundary? So now we have a bit of a challenge. How are we doing for time? Okay, we still have some time. Okay, so the claim is that we can actually solve Abelian-Chern-Simons theory for any compact two-manifold, and it can't depend on very much, since we already said there's no energy scale. So let's think about, we're starting off with a 2 plus 1 dimensional theory. The key thing is that it's a gauge theory, which means, as you've already kind of seen here, it has a huge amount of gauge invariance, or in other words, a lot of the degrees of freedom are not actually physical. So if we had a 2 plus 1 dimensional field theory where everything was physical, we'd probably be sunk. So we should do a lot of gauge fixing. Maybe not so many degrees of freedom. Okay, so essentially the calculation is a series of gauge fixings that I think I will tell you what they are, but they might seem a little, you might have to think about whether this really is legitimate. But we're going to keep transforming this theory until it gets to be not 2 plus 1 dimensional, but 0 plus 1 dimensional. So to start with, to say that it's 2 plus 1 dimensional means that my field, A sub mu, those are functions of, say, x, y, tau. So the first gauge fixing is the one I just did. Let's take so what I mean by that is, if you gave me an original configuration where A0 was not 0, I would construct chi to be minus integral of A0 dt, so that the time derivative of chi, which gives me the shift of A0, exactly cancels whatever A0 was before. So that's our first gauge transformation, which means that the remaining Lagrangian, so already we've made things a lot simpler. We've got minus k over 4 pi epsilon ij ai aj dot. Dot means time derivative. So what happened here was I just used the fact that A0 is equal to 0, threw away all the terms except the term where the 0 index appears in a derivative, which is this term, or this pair of terms. It could be ij, could be xy or yx, and that's all that's left. So this is starting to look kind of interesting. So we still have some freedom left in A1 and A2. So I guess what I will leave for you as an exercise is that compatible with this can add, so we've sort of, if you like, we've fixed the time dependence of chi. We can add a purely spatially dependent chi. Keeping A0 equal to 0, therefore, so to make the divergence of A, so again, this is only spatial components, equal to 0. So let me not do all the details of that. Okay, so we have, let's take a look. What does it look like we're getting close to? Well, if A were not a gauge field but were a particle, then if these were the coordinates of a particle, this actually starts to look like something you might have seen before. So you might think about, suppose we had a particle moving in a constant magnetic field. Because this is where we're going. So we've got two conditions now on A1 and A2, which combined are enough to make all their spatial derivatives equal to 0. So that's why we're almost there. So the equation of motion constraint is that the one I used before. So that is kind of imposed to be consistent with the requirement that A0 be 0. This is the one I claim I was able to achieve by another gauge transformation. So if I combine basically divergence of A in the spatial directions being 0 and curl of A in the spatial directions being 0, then this is what we've achieved, because if you believe I can do all this gauge fixing, then the spatial derivatives of A1 and A2 vanish. In other words, there's only time dependence left. So if you can work through these gauge transformations till you're satisfied, then what we've managed to do is go from 2 plus 1 dimensional fields to 0 plus 1 dimensional, in the sense that these are independent of space. And that is a dramatic statement, because if I've got two things that just depend on time, I can think of those as x and y coordinates of a particle. Then, well, what is this term? Epsilon ij ai aj dot. Well, where have you seen that before? That is this is a constant magnetic field. This would be a constant magnetic field acting on the particle. That is, we know that if we're just doing quantum mechanics and we think about how does a magnetic field enter, the term I'll get if I work in the rotational gauge you can express that as a magnetic field. So the last step, which you might worry about, we've done maybe the hard work, except that we haven't yet set what manifold we're solving the theory on. So we're writing a path integral. We are thinking about classical trajectories of a particle now. So the last step is that right now A1 and A2 are in R. They're just real valued gauge fields, but we are working on a spatial manifold that isn't R2. So it's not quite yet like the particle is moving on the manifold. So far it's like a particle moving on the plane. Is that a problem? Well, the only case I know how to do explicitly is the torus. Then can make one more gauge transformation. You might be sick of gauge transformations now. So, to be, okay, I think in the interest of time, let me not try to show this last one, but it is possible to take a gauge transformation, AJ goes to AJ minus, I'll write it out for you, but not say much more, U inverse DJU. So this is a scalar that I'm getting from some periodic function u, and it's a good enough gauge transformation as long as u is periodic with the periodicity of the torus where I've defined the theory. If I write u as e to the I theta, then this gauge transformation will work with the previous gauge transformations without breaking them if and only if the Laplacian of theta is equal to 0. So that means I should find a function that lets me reduce the a's to living on the torus with Laplacian equal to 0, and that function is 2 pi n1 a1 over L1 plus 2 pi n2 a2 over L2. So finally, this means the particle lives on the torus. And there's a last step. So I claim that what I'm left with is a constant magnetic field. Now I've got a particle in the torus. I don't have any kinetic term. I just have the magnetic field term. And remember that K in front. If I do the counting right, the counting is that K is the number of flux quanta through the torus. We have the classical representation of a particle moving in a magnetic field. No kinetic term. Well, let's put in a kinetic term, because then we know the problem, and then take it away again. So let's add m ai dot squared over 2. So that's my kinetic term. So, and yeah, sorry, I answered a few more questions than I was expecting, so I we'll leave it to you to count that indeed I'm not lying to you, and that K, which was appearing in front of the Lagrangian, so the magnetic field should scale with K, it's actually the number of flux quanta through the torus. Then we have Landau levels. That is, if we had the kinetic term, we'd know how to solve the problem. The lowest Landau level on the torus has K states. Then there are higher Landau levels, whatever, but the spacing between them is h bar omega c, or h bar EB over m, which means that as m goes to 0, I have some degenerate set of K states at the bottom, and all the other states get blown up to infinity. So that is, if we add this term, we get Landau levels. When we take it away, the Landau level gap in energy becomes infinite, so we're basically just left with the lowest Landau level, which means that there's a K-fold degeneracy, GS, and everything else is at infinity. In other words, it's a very strange solution, and actually, the generalization of this won a Fields Medal. I'll mention that maybe briefly, but that is way beyond what I understand the details of. But what happened here for abelian Chern-Simons was that we computed a 2 plus 1 dimensional gauge theory and wound up being able to solve it by reducing it to a particle. That is 0 plus 1 dimensional quantum mechanics. And K, which was the statistics parameter of the field theory, winds up just being the flux through the torus, which tells us the number of degenerate ground states. If I had a more complicated manifold, so the next idea is to say, well, suppose I had something of higher genus like that. I could move the holes far apart from each other. This is kind of a hand-waving argument, but it's the kind of thing where mathematicians like to do estimates and prove it. Imagine doing this. Well, if I move these, if it's really topological, as it has to be, the ground state degeneracy shouldn't depend on whether I move all these things apart. If I move them apart, they probably don't talk to each other. So in general, the ground state degeneracy on a manifold of genus G with G holes is K to the G. Yes, the sphere is non-degenerate, but you'd have to be more clever about choosing the coordinate last gauge transformation to use spherical coordinates.
There are no harmonic functions.
Maybe that's a clue that there's just one ground state. I'm not sure exactly where this... Well, let me just think. Okay, I need to think about what you're saying, but I know that on the sphere it's non-degenerate, and I'm pretty sure you can do a version of this argument to prove that it's non-degenerate. But yeah, the point is, if you like... That's right. There's no function that's going to do that on the sphere. No, I agree with that. But so can you reduce it? Yeah, you can't reduce it to K. Well, that's the point. You can't reduce it to K flux quanta. It's not the lowest Landau level on the sphere. It's just the lowest Landau level on the torus. If I could get the lowest Landau level on the sphere, then that would have a degeneracy. That isn't there. So what you're saying is, yes, a reason why you could not imitate this argument on the sphere and get a degenerate Landau level. So the GSD is K to the G, where K was the quantity, the one parameter in the CS theory, and G is the genus. So the torus is G equal to 1, that thing is G equal to 3, etc. And we can, so this is the topological degeneracy. So there is a degeneracy as long as I'm above the sphere, G equal to 0, no degenerate. So I mentioned before that a generalization of this calculation was important mathematically. There's a famous paper of Witten explaining that if you can calculate Chern-Simons theory on the complement of knots, so R3 minus knot has a deep relationship to a previously known topological invariant of the knot, the Jones polynomial of the knot. Where exactly what the relation is, I will have to refer you to the paper which is called Quantum Field Theory in the Jones Polynomial. So that's Chern-Simons theory. If you look at more complicated manifolds, it can give you much more complicated topological invariance than just the genus. Our simple case, our 3-manifold, was just a spatial 2-manifold cross R, and then we got the genus of the 2-manifold, which is really the only topological invariant of a closed 2-manifold. So to wrap up, let me get the projector warming up and say a little bit about the multi-component case. So what are the checks on all this? Well, I'll show you one big experimental prediction it makes. Okay, so there are various numerical checks you could do. You could look at the number of edge modes. You could look at the degeneracies on compact manifolds. Experimentally, there's a set of checks or attempts at checks that are based on the edge. I don't know of any really in the bulk. But here is the lightning summary of a few of the things I said. So if I want to couple the theory to electromagnetism, then I can integrate out little a to get an effective term for big A. The only thing that happens in that integrating out is that what was k goes to 1 over k. So this is the last thing I didn't show, which is just that it has a quantum Hall effect. You generate an electromagnetic Chern-Simons term if you couple it to electromagnetism and get rid of the little a. This is what I said Wen's theory predicted, that if you go to the edge, there's a chiral boson theory in the one-component case, and this you can measure by trying to tunnel an electron into the edge. So basically, k equal to 1, you get ordinary so-called ohmic tunneling. Ohmic means current is linear in voltage. A prediction of this, which people knew, Kane and Fisher had worked out in the early 90s. If you know a chiral Luttinger liquid like this, and you try to tunnel electrons in, how does the IV curve scale at low voltage? And it turns out that it depends on K. So the most direct experimental prediction that this bulk edge correspondence made was that if you measure the nu equal to 1 state, you will get current linear in voltage. And if you measure the nu equal to 1/3 state and follow through this correspondence, you will get current that goes as the cube of voltage. So it's not gapped, it's not exponentially small, but it's not linear either. So there's some unique nonlinear tunneling behavior at the edge, and some heroic experiments were done to try to see that. This is one experiment by Albert Chang and collaborators. So this is I versus V over quite a few decades in current, and there are power laws, and at least in almost all samples, maybe all samples, it's strongly nonlinear. And in some samples, I is indeed going roughly like V cubed. It doesn't quite agree. There's actually a paper by Shitov, Levitov, and Halperin on the disagreement. So I wouldn't say that we completely understand this experiment, but the 0th order prediction that if you tunnel into the fractional quantum Hall edge, you should see something very different from ohmic tunneling if you're at 1/3. And in fact, it should be closer to I going as V cubed. That kind of 0th order prediction is indeed seen experimentally. So, numerically, this will motivate you to pay attention when Andrei Bernavig is talking about matrix product states. it's possible to use these fairly new numerical techniques to test all this. So you can ask, well, okay, the experimental world is hard. Can you take a large system with a quantum Hall edge and try to study, does it have these power laws that are characteristic of Chern-Simons edges? And this, I think, would be very tough with exact diagonalization. It is possible with matrix product states. So this is work by Daniel Varias, Mike Zalatel, using some techniques developed there. But basically, you put your electrons on a cylinder. They're kind of on the bottom half of this cylinder, so the edge is running in the long direction. It's not running like this. It's running like this. You can make a quantum Hall state that way. And if you do this, I think Andre will tell you about this trick, you get the quantity that is related to the tunneling. So this is an electron correlation function along the edge, falling off with distance along the edge. This power is that 1 over x cubed, which winds up being exactly related to the I going as v cubed through conformal invariance. So at least we can see a power law. So this is what I think is interesting. That is, the dotted line would be what that chiral-Luttinger liquid theory would predict. Again, correlation function is a function of distance, and we see just the right power law, even though the interactions are not model interactions. We can't do full Coulomb interactions, but we can do something that's not too artificial, I hope. So anyway, I present this as a case where now, numerically at least, we can finally check some parts of that theory.
Does it take into account edge reconstruction?
No, this is without reconstruction. So that could be what's going on in the experiment, that there is some degree of reconstruction, and that's why it doesn't perfectly agree with theory. In fact, there are other experiments aside from the tunneling curve that are more strongly suggestive of some kind of reconstruction. I'd refer you to the recent work of Heiblum, I guess, if you want to see some examples. Okay, so I thought to wrap up.
You're getting a bit short of time.
Oh, yes, I forgot that I'm sorry, I'm used to finishing on the hour. Dear, okay. John, you're too polite. I guess we don't have an organizer. Oh, my gosh. Okay, in that case, these are things that I wanted to cover but couldn't, but I hope some of them will be covered elsewhere. And finally, open questions. If you took a 3D topological insulator and filled it partially, what would you get? We don't know. Would you get a fractional 3D TI? What is that? What happens in metals from the non-abelian term of the Berry phase? We only know integer examples, chiral spin liquids. Can we classify gapless topological phases, etc.? So anyway, these first few questions I think are big puzzles that hopefully one of you will solve because they've been big puzzles in the field for a while. I'm very sorry for running over, John. Thank you. Well, now I'm really keeping you from coffee, so I think...
So